Good morning. Welcome to the 40th lecture on economics, management and entrepreneurship. In our last lecture, we had discussed product service strategies and that leads to product focused organizations or process focused organizations. We discussed also after that the problem of plant layout. In that we discussed 4 different types of layout. Today we shall expand on certain specifics of the product and process layout, other layout patterns, and then we shall start a discussion on production planning and control. So, to start with, we shall first relook at what we had done in our last class on plant layout. We said that there are principally 4 layout patterns: product layout for product focused systems, process or functional layouts for process focused systems or job sub problems, the custom products, fixed layout for very big and heavy products, and then a combination of product and process that manifests itself in the form of group layout. This is an example of product layout, which is in a line fashion. The operational sequence and the machine arrangement are the same. In a process layout, different machines or functions are grouped together in the form of a department and they are placed together. In a fixed position layout, heavy and very long or big products are placed in one place, and every other machinery, equipment and people, they serve in one place. This is a fixed position layout. And then we had talked of group layout. In this case, different products, say P1 and P2, they have similar sequences, but not exactly the same sequence of operation. Say for product 1 P1, the sequence could be lathe, drilling machine, milling machine and then goes back. Whereas, in case of product 2, it could be lathe and then milling machine, then drilling machine and then goes back. So, these are arranged in groups or cells. This sort of manufacturing is also known as cellular manufacturing, and the layout is in the form of group layout or in the form of cells. A variation of that is called group technology, where part families are made based on similarity of the design characteristics and of manufacturing characteristics. Design characteristics with regard to size, shape and function, manufacturing characteristics with regard to type and sequence of operations. So, they are like group layout, but there is a difference. The difference is that the machines are grouped in departments, just as they are in a process focused system, but the products flow in a line fashion. This is called the group technology approach. And today we are talking about flexible manufacturing system, where computer aided design, computer aided manufacturing, remote controlled material handling equipment and robotics makes the manufacturing system almost fully automated. And here the human intervention is much less during manufacturing and very high during the design and planning stage, process planning stage. The computer controls the start of the parts from machine to machine as well as the start of the work at each machine. These are different layout patterns, and if you remember, we had discussed a specific problem of product layout and in particular about assembly line. We called it assembly line balancing problem. Assembly line balancing problem, we had taken an example. There are different tasks or work elements with different durations. We wanted to know their immediate predecessors which are given. It can be represented in a network form. A, B, C, D, etc. are the work elements and the operation times or element times are given in number. So, we have to group these operation times and assign them to various workstations such that the precedence relationship is not violated, meaning that B or D cannot start unless both B and C are complete. So, this basic constraint must be satisfied and there should be a balance of the total time for which various workstations are operating. So, we had followed a scheme and with the help of that we had made the arrangement. A, B and C are assigned to workstation 1, D, G, F to 2, H, E, I to 3, and we found that the idle time of various workstations, they vary. The maximum is 14 minutes and the minimum is 11 minutes. That means, workstation 3 will be idling for 3 minutes and 1 idling for 2 minutes, and this is very uneven. So, what we do? We trade and transfer certain stations. Now, what we do here? We have transferred G from 2, G from workstation 2 and H of workstation 3. That means, we have brought H here and G we have taken there. So, G has gone here with 5 as the element time and H has come here with 4 as the element time. Thus, here it is 13 minutes instead of 14 and here it is 12 minutes instead of 1. Thus, the idle time is to an extent of only 1 minute and the total cycle time is 13 minutes and the precedence relationships are maintained. As you will see, D, F and H we can check here. D, F and H, all the three, after D is complete, F can be completed and after F is complete, H can be completed. Earlier D, F and G were put in one workstation. Now, what we have done? We have put G to workstation 3 and from workstation 3 we have brought H to workstation 2. So, 5, 4 and 4 is 13 minutes is spent in workstation 2 and workstation 3 is busy for 1 plus 6 plus 5, 12 minutes. This trade and transfer was done purely based on trial and error method. So, the final allocation of tasks or assignment of tasks to stations are this: station 1 ACB, station 2 DFH, station 3 GEI, and a measure by which different assignments are compared is by finding out the balance delay. Wherever the balance delay is the minimum, that is considered as the best line balancing solution. This is what we had done in our last class. Now, we will now take up the process layout design of the process layout. If you recall, process design is done for customs products. If the company or the enterprise is manufacturing custom products, then various machines are grouped together and they are placed in one department. Now, the question is how the departments should be relatively located relative to each other. Now, the basic principle that is followed in the design of the process layout is to minimize the material handling cost or the internal transportation cost. Now, the cost would depend on two factors. One is the number of trips that is required to be made between various workstations and the volume or weight of the products. Now, these two will basically determine how many trips are made and what is the cost of material handling. Now, we are not going to make a costing of the material handling. It is good if we can make an actual costing. We shall assume on the other hand that the transportation cost or material handling cost is dependent on these two factors, the weight of the product which is transported from one department to another department and the distance between these two departments. Now, since the weights cannot be controlled in the design of the process layout, we will try to minimize the distance that the parts are moving. So, that is the approach we take, and normally once again a judgment based trial and error process or method is used. However, it is backed up by certain objective and graphical methods. Let us see what the methods are. So, basically the objective of a process layout is to minimize the cost of transporting goods between work centers. So, the cost of transportation is sum of xi/di, where I varies from 1 to n is the total number of movements, xi is the measure of quantity, whether it is in volume or weight we have not mentioned, or number we have not mentioned. It is a measure of the quantity moving between work centers, and di is the distance travelled during the ith movement, and a good layout minimizes the distances travelled di, because xi is more or less fixed. Therefore, only di we can control. So, we would like to therefore minimize the distance that the parts move. Now, we will take a specific example to illustrate what we are saying or how to solve this problem. We are assuming that there are 4 different products, 1, 2, 3, 4, and the quantity produced per month are 200, 100, 300 and 200, and the sequence of operation for various products are given. So, you can say that this is an operation, and remember that each operation will correspond to a department. So, A, B, C, B, D, this is the way the product will move, the material will move, so that after the operation D is complete, the product is ready. Product 2 passes through these operations or these departments A, C, D, C, E. This is the sequence. After A, C, then D, then C, then E. Product 3, the sequence is C, B, D, C. Product 4, the sequence is B, C, E. So, there are thus 5 departments or 5 operations, but the sequence in which each product passes is different. Now, what we first do is to have a from to chart. So, these are various departments A, B, C, D, E or various operations A, B, C, D, E. So, from this to this it is moving. So, actually these are two tables, one is up to E up to this place and the second table is from A, B, C, D, E to this. So, let us look at the from to chart. This is called a from to chart. So, from A it is going to B and the amount is A to B, the quantity per month is 200. So, this is 200 A to B. Then A to C product 2 is moving, the quantity is 100. So, it is 100. Then B to C and D, let us look at that. B to C, the quantity moving is 200 and then once again here product 4, it is going from B to C 200. So, 200 and 200. B to C 200 and B to C, this one is 200. Then there is also a flow from B to D, look at that. B to D, here is this one is 300, product 3. So, B to D, this is 300 and is there any B to D? Here is one, B to D, it is 200. So, B to D is 200 here. So, like this we have written down the quantity moving from one department to another department. Now, you see here A to B is, we are now not considering whether the movement is taking place in a reverse direction. For example, there is a movement from A to C, A to, no, let us consider this, B to C 400, 200 plus 200, 400 quantities are flowing and then C to B there is once again 200, C to B here this one, C to B is 300, this is here and C to B probably is, there is another one somewhere, C to B is here, it is flowing 200. So, this is C to B 200 and once again C to B 200. So, these are 500 and earlier we have seen B to C 200 and 200 400. Therefore, the distance moving, the quantity moving between B and C in either direction, whether from B to C or C to B does not matter, in either direction the total movement is 200 plus 200 plus 200 plus 300. So, that comes to 900. So, the travel chart is basically a consolidation of the from to chart where the direction of movement is disregarded. Thus, this 900 shows that the amount travelling between B and C in either direction is 900. So, from here we can derive the travel chart. So, A to B is 200 because there is nothing from B to A. A to C is 100 because there is nothing from C to A. B to C is 900 as I have calculated. B to D is 200 because there is nothing from D to B. Now, come to C. C to A there is nothing because A to we have already taken care of C to A, therefore, this is an upper triangular matrix. There is nothing in the lower below the diagonal, is all the points, all the values are coming above the diagonal. For example, C to D is C to B we have already taken care of when we considered B to C, D to A, B, C we have already considered when we considered A. Thus, these are all zeros. So, here we have C to D, C to D is 100 and D to C is 100 and 300. So, total 500, 100 plus 100 plus 100. So, this is 500 here, C to D. And then finally, between E and C, just one second, I might have made a mistake here. C to E is 200 here and C to E is 100 here. Thus, C to E is 100, C to E is 200. So, C to E is 300 and between C and B, let us see how many, C and B 200 and C and B 300. So, this entry is okay, 500, sorry, this is okay, but between C to E it is 100. Now, we are considering D to E, okay. Now, D to E there is nothing, C to E is 100 here and C to E is 200 here, all total 300. So, that is what we have written C to E 300, but we should have shown it here. C to E is 100 and C to E is again 200, that is missing. So, there should have been another here. Yes. So, that makes it all right. Now, C to E now is 300 and that is what we have done here. So, now we have the quantity travelling between different departments are now plotted here, are now calculated here. So, what our strategy would be that if between A and B the amount travelling is 200 and between C and D the amount travelling is 500, maximum is B to C is 900, then B and C should be as close as possible to each other. Followed by C and D the amount travelling is 500, therefore, C and D should be as close to each other as possible. Now, D is not connected with A, B and C. D is not connected with A, is here, not connected with A. Therefore, D can be away from A, but cannot be away from B or C. So, this is the way we do. So, what is now done is that from these values we construct an initial graphic solution, where we show almost in a linear fashion first of all the departments or operations. So, these are A, B, C, D, E and the quantity travelling between various departments are written down here in the along the arc that joins these nodes. So, between A and B the amount travelling is 200, between B and C 900, C and D 500, A and C 100 and C and D 500. Now, let us put them as close to each other as possible. Now, this is one way in which we can put it. A and B, they are close to one another, each other, and A and C is also close to one another. So, instead of putting them in a linear fashion, we put it here, because this distance is 100, it can afford to be a little longer, and C can be close to 900. D can be somewhere here, because E has to be close to C 100, C can be here. So, this is a purely heuristically we can put the relative location of the departments. So, the ones that carry highest amount of material, they should be as close to each other as possible. The one that carries least, they can be little away, the diagonal distance is higher than this distance. So, this is a purely based on judgment. Now, we consider the amount of space that is required for every department. Now, there are different considerations. Firstly, the machine consideration, material consideration, people consideration and aisle that must be left between machines for movement of material handling equipment and for persons. So, every machine has a volume and a certain machine also needs to travel a little. Then for machine maintenance and for other plant services, we need some space. In fact, they should be calculated. For materials, materials have to be received and between different machines in process inventory is built up, a space must be available there. After the work is completed, space must be there for storing and shipping them, and if there are wastes and scraps, they must be stored and shipped. Additionally, we also need space for tools, jigs, fixtures, dies and maintenance materials. Then there is a space required for movement of the operator, for operator himself and even for material handling equipment, and there must be some path or aisle left for a person to move and for material handling equipment to move. All these are required to calculate the space requirements, and there are standards. If it is a forklift, then how much should be the aisle space, aisle width, etc. If it is some other thing, then what should be the aisle. There are standards that are available for various machines and for various aisles. Once the space is estimated for every department, we already know the relative location of A, B, C, D, E. Now, the space requirement for A could be this, for B it could be this, for D it could be this, for C it could be this, E it could be this. So, first of all, we make an initial block diagram with estimated areas. Now, you can see that this is very irregularly shaped, but the actual shape could be a rectangle or could be a square. Hence, one has to now reconfigure this diagram so that this total area remaining same, it is something like a rectangle or a square. That is what we have done here. So, we have keeping the relative location similar, we have tried to accommodate it within a rectangle, and this is the block diagram considering rectangular buildings shape. Now, this is a high level design. One can of course decide where should be the aisle, how the exact machines in the department D should be put, whether it should be linear fashion or it should be a U separate thing. These details time does not permit me to discuss the details of how the machines in a particular department should be laid out, where the entry and where the exit should be, where the material handling equipment should move, where should be the space for wastes, for finished products and for in process material, where is the place for tool room, etc. We are not discussing these details, but we have now at least discussed in the context of process layout how relatively the departments should be laid out. Now, the basic consideration is the load that is transported from one department to another department, and wherever large amount of load is travelling between two departments, those two departments should be as close to each other as possible. So, this is the principle that is applied, and there are various software packages such as Craft and other such packages that can be used to help a designer of a process layout problem. So, friends, we have now discussed different layout problems and two specific assembly line balancing and process layout design problems we have discussed in some detail. Now, we shall take up the production planning and control aspects of an enterprise. So, the topic that we are now starting is production planning and control. Now, before an enterprise starts manufacturing a job, first thing to do is to plan for production. Naturally, planning would require annual plan, monthly plan, weekly plan, how much to produce. Then each plan must be broken down into schedules that says that this machine should be loaded at this point of time for this particular job, and the job must be completed at this time on this day, the next job should start. These details are who will do the job, which operator will do the job, how the job should move from one department to another department, who is going to authorize the operator to start the work, how much material should be procured from the stores, which tool should be used, all these are planned in advance, and this is usually done by the production planning and control department. This is like the nerve center of a manufacturing organization. So, let us study what the different functions of a production planning and control department, fondly called PPC department. Let us see how it functions. Firstly, a definition. Production planning is concerned with translating overall sales orders and plans to specific schedules and meeting them by efficiently coordinating and integrating the factors of production. So, the input to production planning, basic input is sales. However, to be able to meet the sales that the company has, the demand or the order that the company has received, it has to know what its present machine capacities are, material, how much of raw materials it is having, whether it is already having certain finished product inventory of that product, how many people are available, whether certain machine has broken down, whether the tools that are required are available for the product, I am saying for manufacturing of the product. So, these details the production planning control department must have in order to commit how much it can produce and deliver to the stores for final shipment to the customers. So, a lot of information must be available. Once this information are available, the next question is how best the information can be utilized to prepare a plan. Normally, as we shall see, a lot of mathematical tools are available to help formulate a planning problem and solve it. Some of them take the problem as a static problem, given a particular order how to solve it. Some of them take it as a dynamic problem, things are changing, the sales are changing with time, the inventory are changing with time, machine availability is changing with time. Some consider only the production planning as a problem, how much to produce, and some consider not only production, but also production and distribution. Some consider the planning as not to just produce, but produce how much of overtime to be used, how much of subcontracting should be used, whether one should go for additional number of workers or it can lay off certain contract workers. Now, these details which were normally done or which for a long time or are still being done in some companies completely subjectively are now being done mathematically using mathematical models. Now, time does not permit us to go into those mathematical models, but we shall definitely give you an idea as to how such models are made. Now, let us consider these details now. The functions can be, production planning functions can be grouped in 5 headings. Production planning proper, which is I am calling programming, product analysis and routing, scheduling and loading, authorization of production, follow up and control. I think I should add here another point, that is control. Now, first programming. Prepare production forecast from sales forecast. Make master production schedule. Plan material procurement, how much raw material to procure. Prepare a schedule of personnel, how many people are required every month. Make a schedule of operating capital, how much, something like a budget, how much money we require, and plan alternative strategies. Now, this is a programming function, these 5 or 6. Master production schedule almost looks like this. It is made for the whole year, something like an annual plan, month wise, January, February, etc. up to December. These are the departments. In terms of the output of the department, it specifies how many units are expected as output from every department at the end of every month. So, the department head knows that at the end of the month how much to make. This is an ultimate output prepared in the programming function of PPC as a master production schedule, MPS. Now, we shall take off a situation when the demand fluctuates almost seasonally. Now, when demand fluctuates, then it influences demand by price cutting. The company can cut the prices if the demand is less, it can cut its price in order to induce the customer to buy more, so that the fluctuation is less. expand product line by including products with less demand variability. Already we know this product line diversification. To meet seasonality in the demand, a company can have more number of products, product type, such that the variability, the total aggregate demand, variability in the total aggregate demand is less, or it can meet the high demand by producing more and keep it as inventory in the lean time, or it can go for overtime or using part time workers or can subcontract. It can also go for aggregate planning. So, almost these things we have discussed earlier. This is a new term, aggregate planning, which I have introduced in the context of production planning and control. Let us study that in some detail. Aggregate planning is usually done for 1 year. It aggregates all types of products. It does not make specific plans for individual products. Instead, it aggregates all types of products and expresses it in terms of tons or units of output. It aggregates all types of workers in terms of labor hours and all forms of facilities in terms of machine hours. Thus, it forecasts only in aggregate terms, not specific product type, all products put together. What is the forecast? That is why the name aggregate planning. Estimates variations of costs such as inventory, payroll, layoff hiring, production change, etc. And thus, for actual planning of production of individual products, one has to go for a second stage planning. Now, let us see how it is done. Normally, it assumes that the costs vary either in a linear fashion or in a quadratic fashion. For example, workforce increases. As workforce increases, their wages increase. It is linear. Now, suppose there is a possibility for an enterprise to either lay off workers or hire more workers, then the workforce change has an effect on the wage payment, and it usually goes up in a linear fashion in this fashion, and in this fashion if it is laid off, you will have to also give them more amount of money to lay them off. Just as if you hire, you get pay more. So, this sort of structure can be approximated by a quadratic cost function. When one pays overtime to increase production rate, then also it goes up, and that also can be approximated as quadratic. And inventory normally has got a minimum at a particular value of inventory, the cost is the minimum. We shall consider this in more detail when we discuss about inventory control, but at this moment take it for granted that if inventory increases, the value associated with it increases, and if inventory is less, then also the value increases because of opportunity cost associated with it. So, all the costs, at least these 4 costs, the production rate change, the inventory change, the workforce change, can be approximated as quadratic, and this cost remains more or less linear. So, aggregate planning, what it does, it gets the forecast for the next period. Already we have discussed how different forecasting methods can be used, and it uses these cost functions, and it gets information regarding inventory, workforce, production, etc., and uses a decision model to calculate the cost resulting from the decision, and it tells how much inventory should be built up, how many workforce to deploy, and what should be the production. So, there is a mathematical model, usually it is a quadratic problem, and one can find out this value. It is given in much more elaborate form in this fashion. For every period, period 1, 2 to period n, forecasts are made and initial condition is known, and all the costs that result, they are added up here. Now, the decision is made and then fed back. This decision is fed back for period 1 and then fed back to period 2 and then fed back to period n. So, a model that is made for the n period, it is basically it takes the complete model and then solves it. This is the structure of an aggregate planning problem. I did not discuss this in more detail because it is quite complex, the model is quite complex and it is difficult to discuss here at this stage. However, we shall consider a small problem of product mix problem. A product mix problem says that we have different products and how much of each product should be manufactured, so that it maximizes the contribution to profit and satisfies the constraints. This we will take up right away. Let us take this example. A manufacturer produces 4 types of household products fabricated from sheet metal. So, there are 4 products. Finally, we are asked how many units of each of these products are to be manufactured, of course, to maximize the profit. The production rates in hours per unit and available production hours are given or are known for different departments and given on the next slide. What are also known are their selling prices, variable costs, minimum and maximum sales, that are given in the next slide. Furthermore, the sheet metal available is 2000 square meter, which are used for products 2 and 4, and product 2 and 4 require 2 square meter and 1.2 square meter per unit each. So, there is a constraint as far as the sheet metal is concerned. Now, look at this table. It says that each product passes through 5 departments: stamping, drilling, assembly, finishing and packaging, and the time it takes in different departments are given. TS1 stamping product 1, TD1 drilling time for product 1, TA1 assembly time for product 1, etc. So, accordingly, of course, the numerical values are not given, symbolically the values are given here, but the actual values are given or have to be known. And in a year or in a month, whatever is the time for which we are making the plan, stamping time available is Ts, total time available in that, let us say, month. Drilling time in that month is Td, assembly time Ta, finishing time Tf, packaging time Tp. So, you can very well understand that suppose we produce product 1 x1 in number, product 2 x2 in number, product 3 x3 in number, product 4 x4 in number, then the total time consumed for product 1 in stamping is x1 into Ts1. Product 2 takes x2 into Ts2 time, x3 into Ts3, x4 into Ts4, and all this time in stamping must not exceed the total time available Ts. So, this is a constraint, x1 Ts1 plus x2 Ts2 plus x3 Ts3 plus x4 Ts4 should be less than or equal to Ts. Similarly, for drilling, assembly, finishing and packaging. This is what I have written down here, machine constraints. Okay. This should be less than or equal to TSI, etc. 4 products, Xi is the number of products of product type into TSI, Xi, TDI, etc. Now, there are other constraints when you come to this table. The minimum sales and the maximum sales for each product type is given. That means, the constraint is that x1 should be between S1 and S1 minimum and S1 maximum. x2 should be between S2 minimum and S2 maximum, x3 between S3 minimum and S3 maximum, x4 between S4 minimum and S4 maximum. That is we have written down here, sales constraint. That is, Xi is between Si min and Si max. Now, there is a material constraint, if you recall, product 2 and product 4, 2 and 4, they require a particular sheet metal, available volume is 2000 square meter, available area 2000 square meter, and each unit of product 2 requires 2 units, product 4 1.2 square meter. So, 2x2 plus 1.2x4 should be less than or equal to 2000. I have written 2000 equal to 2000, it should be less than or equal to. Please make a correction here, it should be yes. This is the material constraint, and there is another restriction called non-negativity restriction, that each Xi must be either 0, that is do not produce, or produce something. Xi should be greater than or equal to 0. So, we have machine constraints, material constraint, sales constraints and non-negativity restrictions, and then what we are supposed to do? We maximize an objective function, which is maximize the contribution. Contribution is the price minus the variable cost, that is the contribution from the ith product. Xi we are producing sum over I equal to 1 to 4, that should be maximized. I think we do not have to write twice, we can take it out. So, friends, basically what I did so far, in the beginning I completed whatever I wanted to discuss in plant layout, and then I started a discussion on production planning control. Two things I said under programming aspects of production planning and control. One is aggregate planning, in which I said that irrespective of the type of product that a company is producing, type of machine it is having, type of workforce it is having, it makes an aggregate plan and it tells how much to produce of all demand, all products put together, or how much workforce it can hire or it can deploy, no matter where and how much to produce. We only gave the model structure without going into the details, but next we introduced a product mix problem. How many products of each product type should be produced under certain constraint, and this is called a linear programming formulation. The objective function, which was to maximize the contribution to profit, was linear, and the constraints were also linear. Standard linear programming packages are available to solve linear programming problems. If one solves this problem, it will give the optimal values of x1, x2, x3, x4, meaning it will say how many products to manufacture of each product type. Production planning control and control literature is rampant with various mathematical models, static models, dynamic models, that considers every period as one stage. It can assume deterministic demand pattern, or it can assume stochastic demand pattern. That means demand changes with time with a probability distribution. There can be different other types of constraints that can be taken. A systemic outlook can be taken of production and distribution, whereas one can only discuss production. So, production planning and control literature is rich with different mathematical models. We do not have time or scope to discuss these mathematical models, but we have introduced only the most basic ones. In our next class, we shall discuss on scheduling and other functions of production planning and control. Thank you.